So let's look at an example. So here's an example. I just generated some data. The target function is the horizontal flat line. You can see the boundary between plus and blue and red. I generated a bunch of data. I ran that algorithm. Now I can't solve it by hand anymore. Okay, when I ran the algorithm, it produced this thick black line, and the corresponding thickness is illustrated by the gray lines. And you can see that as you increase the sort of cushion around this thick black line, it simultaneously hits these two blue points and that red point. What's interesting is if I throw away all the other blue points and all the other red points, I would get exactly the same separator. Wow! Okay, wow. Okay, so I identified not only the optimal separator, but also simultaneously the important data points. Now, this algorithm is in some sense deterministic. Once you give me the data, boom, the optimal fattest separating hyperplane is unique, it's well defined, you can find it with quadratic programming and all the good stuff. Okay? Now let's see what would happen if we ran PLA. Now, because I know the target function, I can compute E out. So you can see that E out for this optimal separator is not quite 0. To be 0, you need the flat red guy. Now we can run PLA, and PLA picks a random data point, and at every iteration, picks a data point that's misclassified and updates and goes, and eventually separates the data. So you could get, now follow my mouse cursor, you could get the separator that looks something like this, or you could get the separator that looks something like that, okay, or you could get the separator that's close to the target function. Okay. And that depends on the order in which you present the data, which random misclassified point you take at each PLA iteration. So there's a lot of randomness in the PLA. And that means that the final hypothesis you produce is in some sense a random final hypothesis. It separates, but it could be anything. And so on the right, I'm showing you the E out for the support vector machine. And that's deterministic in some sense. Doesn't matter about order, nothing. Okay. It's just a quadratic program. Okay. And then if you run the PLA, you get a whole bunch of separators, and if you're lucky, you can get a separator that has better out-of-sample error, okay? Depending on the order in which the data points pop up. But if you're unlucky, you can get a separator that's much worse. Okay? And they're all separators. They all have the same E in. Okay? So, support vector machine, is this nice, stable, robust classifier. Okay? And, the PLA would give us this array of classifiers, final hypotheses with a wide variety of out-of-sample error. That's just a comparison of the support vector machine with the perceptron learning algorithm. Both of them produce a separator. The support vector machine is in some sense the most robust. Now, let's link the robustness of the support vector machine, which we have so far intuitively argued, let's link it to regularization. So I'm going to just end on just a slide that shows the analogy. Okay, the support vector machine says, I'm going to minimize the norm of the weights. That was the program, the quadratic program, the optimization problem that we just had. I'm going to minimize the norm of the weights subject to the constraint that you fit the data. So find me the most robust separator. Okay. When we studied regularization, remember we talked about let's give ourselves a weight budget, okay, and we'll minimize the in-sample error subject to that weight budget. So now let's put this in this table and compare. Regularization says minimize the in-sample error, okay, subject to a budget. So in some sense, you can think of the optimal hyperplane as, optimally regularizing. So using the smallest possible budget while trying to get the in-sample error 0. Think back to Occam. Use the simplest hypothesis that explains the data. So this is in some sense, the optimal hyperplane is in some sense a literal implementation of Occam's razor. And you see the similarity. In both cases, we're trying to sort of constrain the complexity of the final hypothesis. In the support vector machine, in the optimal hyperplane algorithm, we're explicitly minimizing the complexity. In the regularization approach, we are minimizing the in-sample error while I give you a budget of complexity. So you see the similarity and the link between the fattest hyperplane and regularization. But we arrived at the fattest hyperplane intuitively as its most robust to measurement errors in the data. Okay. So now we have multiple reasons why we think that the fattest hyperplane is good. It links to regularization, it's most robust to measurement errors in the data. Okay. So can we in some sense investigate that in a more quantitative, more principled manner? So this lecture was spent on the algorithmic issue. Okay. So we intuitively sort of justified the fattest hyperplane as the one that's most robust to data and asked, can we efficiently find it? The answer is yes. Okay. And we can even get more efficient than quadratic programming, because quadratic programming in very high dimensional data and very large amounts of data is essentially an n cubed algorithm, where n is the number of data points, and the proportionality constant in that order of n cubed is related to the dimension. Okay, so it's dn cubed. So even though it's a finite algorithm, just like the pseudo inverse algorithm for regression, we now have an exact algorithm for classification. Even though it's a finite algorithm based on convex optimization, it's still not necessarily very efficient. Okay. So a lot of research is done on making it more efficient, and we'll talk a little bit about that later. Okay. Especially when you go to high dimensions, it can get extremely costly. But now we've at least established the feasibility of being able to find the fattest hyperplane efficiently. Okay, so let's now, next lecture, talk about, is it the case that the fattest hyperplane or fat hyperplanes in general are better than thin hyperplanes? Next time. For now, checking out.